Hi everyone, so this is lesson 3 of chapter 10, electrical circuits. We will be looking at what potential divider circuits are. We'll also look at potentiometers at the end and how they can be used as potential dividers. It's a very important part in terms of PAGs actually, and how we connect certain components and why. We will look at potential dividers in circuits that have variable components, so like LDR, thermistor, variable resistor. We will also look at these equations and how to derive them and get to them, and techniques and procedures used to investigate potential divider circuits as well. So this is more of a practical application and how you can test it, which is quite simple to follow. Okay, so what is a potential divider circuit? A potential divider circuit has two resistors in series. So I have two diagrams here, diagram 1 and diagram 2. They show exactly the same thing, it's just simply one uses a cell, the other one has a power supply, and instead of them being too close to each other like the cell, they're just apart in that way. So usually this is the more standard structure that you will see in exams showing potential dividers. So it contains two resistors, they're in series, and they're used to split or divide the potential difference of the supply. So whatever we give in, these two resistances in series split the potential difference in different portions depending on the resistance, so that a chosen voltage can be provided or a chosen potential difference can be provided to another device or circuit. I will clear out the highlighting so that it's a bit clearer to see what I will be explaining. So what we have is potential difference in, and using Kirchhoff's second law, we know that the potential difference will have to be shared between the two components. So using his second law, across the closed loop, so sum of EMF is equal to sum of potential differences across a closed loop, which means that V in should be equal to V1 plus V2. In this case, we call V2 the V out. The idea is that this circuit, this potential divider circuit, this part of the divider circuit will be providing a different output, potential difference output, to a different circuit or device within a component, within a specific device. That's usually used in speakers. It can be used in ovens, in so any sensing circuits, so circuits that have to have change their resistance with light intensity, or circuits that change their resistance with heat changes. So we will see that as well, but this is the simplest form of it with fixed resistors. So like I said already before, not every circuit that we use is simple. These are simple circuits. So in this case, sometimes we will need to feed from a simple circuit, we will need to feed a potential difference, a specific amount of potential difference to another circuit for them to do a specific job. For example, we can only turn on a light if the output of the voltage is 6 volts to that feeding into the second circuit. So that's just a little bit of a brief intro to what it can do. And this is just another diagram of showing it as well. So we already spoke about what it does. So a potential divider, just like the name suggests, divides the potential difference of the supply in a different ratio. So if we have a look at this diagram here, the V out will depend on the resistance of resistor 1 and the resistance of resistor 2, as well as the potential difference that we give into the circuit as the V in, the EMF basically. If a resistor has high resistance, it will get more potential difference. If they both have equal resistance, they will split the V in equally. This happens due to the Kirchhoff's first law. So in Kirchhoff's first law, we know, this is the positive terminal, we know that the current has only one loop to flow through. So the current through resistor 1 will be the same as the current through resistor 2. If I write this down in terms of an expression for what happens at each one of them, so V1 and V2 as well. So if we say that the potential difference across R1 is V1 and the potential difference across R2 is V2, I can come up with two expressions. So I is V1 over R1, and I is also equal to V2 over R2. Remember, I'm just using this equation and I just rearranged it. To rearrange, you just simply switch the positions of R and I. So, since the two expressions have the same current value, I can equate them together, and I will end up with V1 over R1 is equal to V2 over R2. If I rearrange this equation, I can come up with an expression of V1. So if I times, let me just do it step by step. If I times both sides by R1, I will have V1 is equal to, so this one and this one, R1 divided by R1 is 1, so we can get rid of it. It will be V2 R1 over R2. Then if I divide both sides by V2 divided by V2 is 1. Once again, we get rid of it, and I come up with the expression of V1 over V2 is equal to R1 over R2. So if I had a potential divider circuit and I was given V1, R1, R2, I could be able to rearrange the equation to get V2, so the potential difference across resistor 2. And that's due to the fact that they both have the same current going through them. Now, how can I use other values to get through to this one as well? Well, the same thing can apply in terms of current going through the whole circuit. So the total current, which is the same as the current going through R1 and R2, can be linked to the total resistance of the circuit. So, and the total potential difference in the circuit, which is V in. So I'll write another expression for I in terms of the total potential difference in the circuit and the total resistance in the circuit. We know that this is a series circuit. R total is equal to R1 plus R2. So that leaves me with V in over R1 plus R2. Since I know that in most of the potential divider questions, you will need to either calculate V out, so the potential difference that you're feeding into another circuit, I will write my expression, instead of using V2, I will write it out as V out. So I is equal to V out over R2. The reason I'm proving this equation, which I'm going to show you in a second, is because sometimes people confuse which resistor to use over in the potential divider equation, and this is to avoid that confusion. So it's easier to work it out yourselves. So yeah, I will equate these two current expressions. So that will be V out over R2 is equal to V in over R1 plus R2. In the case that we wanted to calculate only V out, I need to get rid of R2, so I'll multiply both sides by R2. And that leaves us with V out is equal to V in times R2, because R2 divided by R2 is 1. R2 divided by R1 plus R2. Now this equation is given to you in the formula booklet. As you can see here, you're given both expressions that are proved. They're both based on the fact that current is the same everywhere in a series circuit, since there's only one path for it to flow. And you can already see that it's telling you R2 over R1 plus R2 in the equation. But many people always miss out what this R2 is. Now this R2 is the value of the resistance of the resistor that accompanies the V out. This expression only applies to two components in series that feed off another circuit, but it could also apply to a circuit that has three components instead. It's not very different. If you had three components in series, then you will just simply have to add a third component at the bottom and take it into account, depending on what you're using. But we will see example questions in class as well regarding this. So if we look at this quick diagram, it shows the resistances of two resistors in a potential divider circuit. It gives us V in, and we need to calculate V out. So to calculate V out, to calculate V out, you can use the equation straight away that we just derived. R2 V in. This is the point. This is the part where people get confused with what's R2, what's R1. Well, the V out is always linked to R2, so the resistor that gives the output potential difference that we need to get. So now it gets very simple. We have 270 divided by 270 plus 170 times the potential difference in, which should give you 22 volts. So we know that the V out is 22 volts, and if we wanted to find out how much potential difference across this resistor, which is a lower resistance, so we should expect to have a lower potential difference across it, you use Kirchhoff's second law. So we have 36, the sum of EMF is equal to the sum of PD, which is equal to 22 plus the potential difference across the 170. So that's the potential difference across the 170 ohm resistor is 14 volts, which is as expected because it has low resistance, lower potential difference, since R is directly proportional to voltage as current is the same through both resistors. Okay, so far we talked about potential divider circuit with components. We have also talked about the potential divider equations that you need to know. Now we'll talk about how potential divider circuits with variable components will work if we had an LDR, a thermistor, or a variable resistor. So we have seen how it will work with fixed resistors. So we will have a fixed V out being fed to another circuit. What if we wanted to change V out though? What if we wanted to have the potential difference output fed into another circuit to be changing depending on certain values or variables? Well, we could use in the first diagram here, I drew a circuit with a variable resistor as R2. So if I change the resistance of R2, so for example in here, if I decrease the resistance of R2, that will mean that you will have, since R is directly proportional to V, then V out will also decrease. If I increased it, the opposite will happen, the V out will also increase. So I can control the V out and in terms of increasing and decreasing the resistance of the variable resistor. Now, if we look at, so this is circuit 1, let's go to circuit 2. If we look at circuit 2, we have a thermistor connected to it. That means that we know that the thermistor's resistance varies with temperature, sorry. So you know that the thermistor's resistance varies with temperature. So if the temperature increases, we know that the resistance decreases. This is a good point to remember this graph of resistance against temperature. So as we increase in temperature, the resistance decreases because you have more free electrons moving, so the number density increases, right? And since the resistance is directly proportional to voltage, if resistance decreases, voltage also decreases, the V out also decreases. If I done the opposite, so if I decrease the temperature, then the resistance will increase, which will mean that the potential difference increases. This can either turn off or on a second circuit, depending on how it's connected. It could be in heater sensors, so they sense the temperature that the room is in, and they will either start or turn off the heater depending on that. It's used in hair straighteners or ovens or things that operate with temperature. So then we also have another setup here, circuit 3. Now with circuit 3 we have an LDR. The LDR's resistance varies with light intensity. So if the light intensity increases, we know that the resistance decreases because you have more current now, since there's more free electrons. We also know that the resistance is directly proportional to voltage in the potential divider circuit, which means that the voltage V out will also decrease as well. However, what about if we didn't have the V out connected to the LDR? What if we look at diagram circuit 4, which shows the V out being on the fixed resistor instead of the LDR? Well, in this case, we will have, as the light intensity increases, we know the resistance across R2, so the LDR, will decrease. This means that the voltage across V2 here will decrease, which means a greater proportion of V in will go to the fixed resistor so that means that V out will increase in this case, since you have less potential difference from Kirchhoff's second law. You have less potential difference being given to V2 than V out if the light intensity increases. So depending on where the V out is, we have to figure out how it works around it. I will do another example here as well. Okay, so we have this diagram. It has a thermistor and a resistor in series, and the V out of this potential divider circuit is across the thermistor. It gives us the values for V in, which is 12 volts. It gives us the value for V out, which is 10 volts, and it also gives us the resistance of this fixed resistor, which is 2.2 kilo ohms, or otherwise 2200 ohms. So what we need is our equation. You could do it in a different way as well. If you want me to do that in class, let me know. So you will have the resistance of the thermistor that you need to calculate, divided, since this is the V out across it, plus the resistance of the thermistor plus 2200 times the V in, which is 12 volts. So I will write it down. I will rearrange for R before I put any numbers in. So let me just delete that and put the numbers in after, because it's always nicer to keep it neat until the end. So we have V out times, so I'll times both sides by R of the thermistor plus the R of the fixed resistor. Let me just put it in different color. So I'm timesing both sides by it, which will leave me with this expression. That's because RT plus R divided by RT plus R is 1. So I will expand the brackets, which will be V out R of the thermistor plus V out R of the resistor is equal to R of the thermistor times V in. I'll take all the resistance of the thermistor expressions to one side. So that will be V out R is equal to V in minus V out RT. Then take RT as a common factor. So that will be and now I can just divide both sides. Let me just do that with different color by V in minus V out. So I'm just simply doing calculations to eliminate certain values that I have to make my life simpler. So that will be V out times the resistance of the resistor divided by V in minus V out, which gives us, once I start placing the numbers in, V out is 10 times the resistance of the resistor 2200 divided by V in minus V out, which is 12 minus 10. So what we have is 22,000 divided by 2, which is 11,000 ohms. So now we have seen potential divider circuits with LDR and thermistor as well as variable resistor. This is the last bit I'll talk about in this lesson and this chapter. It's about potentiometers and how we can use them as potential dividers. So this is how a potentiometer looks like. So this diagram here. It's basically a variable resistor, but it has 3 terminals and a sliding contact. So it's got terminal A, terminal B, terminal C, and this is the sliding contact that you get to move back and forward. This black part of it is actually a very tightly coil of wire that provides you the ability to change your resistance based on the length of the wire and where you're moving the sliding contact from. Now, when you move the contact, so this is a diagram, this is how we represent a potentiometer in a circuit. And since we already know that a potentiometer is quite similar to a potential divider because it splits the current to the potential difference to what we want it to be from V out. The only difference between potential divider circuits and a potentiometer is that with the potentiometer you can move the contact towards A, for example. So if I move it towards A, the V out will increase until basically V in is equal to V out. So you can reach the maximum potential difference of the circuit to be equal to the EMF that you provide the circuit with as V out. However, if you move the sliding contact to B, so to the very end of the potentiometer, then the V out will decrease until it's 0. So that means that a potentiometer allows us to alter V out from 0 to maximum potential difference, which is V in basically. With the potential divider circuits, we can't do that. With the potential divider circuits, if you have a fixed resistor, that resistor will always get some part of the V in. So it will have, you won't be able to get a 0 V out or a maximum V in, maximum V out to be equal to V in. And that's because you still have a fixed resistor that still shares some of that value. So with a potential divider circuit, you can't get 0 voltage as your lowest voltage out, and you can't get your maximum voltage to be equal to V in, because it will always share some potential difference with the fixed resistor that's placed there, whereas with a potentiometer you can't do it. This is a skill for practical work, especially when it comes to exam. There was an exam question before, from what I can remember, that did ask why is it better to use a potential divider circuit than potentiometer instead of a variable resistor. And I did mention it, I think it was in chapter 8 or 9, I did mention that we'll come back to this. Well, this is the reason, this is the last part that you do need to know in terms of electrical circuits, and obviously a lot of practice of questions. But the most important part is this, that a potentiometer can give you a range of values for V out, starting from 0 to maximum V in, whereas in the potential divider circuit, you can't get from 0 to V in. You can get a specific range, but not from 0 to maximum V in. I hope this helps, and if you have any questions, please do let me know.